Alright, so today we'll be considering the following example, which is pretty much the very last example in the root locus topic. And consider the following feedback system where we have a proportional controller K used to control the plan 10 over s times s plus 1, s plus 6. And we would like to find the K value such that the closed-loop system is approximately second order with omega d equals to 1, which is the damped nature frequency. And in part B, we would like to find the K value such that the closed-loop system is approximately second order with psi equals to square root of 2 over 2, the damping ratio. So first of all, both of them are under damped responses, and apparently this is this is a third order system, so we want the system to be approximately second order. So there should be two dominant poles and a third pole that's far away from the other two poles. That should be the case. So let's start with writing down the open loop transfer function. It is equal to k times 10 over s times s plus 1, s plus 6. And what we would like to investigate is the closed loop transfer function, and more specifically, denominator of the closed loop transfer function. Right, so if I can write the denominator of the closed loop transfer function, it will be something like this, right? So denominator of g closed loop of s will be equal to s cubed plus 7s squared plus 6s plus 10k, right? And this will be give us the closed pole locations. And I would like to put that in a format such that I can write this thing as d of s plus, let's say, k times n of s. All right, so since this is k, I would like to change it to, let's say, k bar times n of s. Okay, and what I would like to do is this basically. So I would like to call this part as d of s. Okay, and what I would like to do is that since we have done the cases when n of s is equal to 1. In the previous examples, we have sketched the root locus for n of s is equal to 1. So I will do the same here. So I will, instead of 10k, I will write here as k bar times 1. But maybe I can do it more cleaner this way. So I will write this thing once again. Okay. So I will write this thing once again and call 10k a k bar. Square. Maybe it will be more evident or more clear that way. It's k bar. Okay. And I would like to write this thing as ds plus k bar times n of s. So here I will call this guy as d of s, and I will say from here n of s is equal to 1. Alright, so, and if I can write down this in this format for ds plus k bar times n of s equals 1, I can sketch the root locus if I know the roots of n of s and d of s. So let me do that as well. And I can also define this k bar as, let's define this guy as k bar is equal to 10k. That's how we define it. And the corresponding root locus will look something like this, right? So if we go over there, this is my real axis, this is my imaginary axis. And I have the pole locations as this has the pole at the origin at -1 and -6. So I have here -1 and somewhere here -6. Maybe I can put it a bit earlier so that I can put some part of the root locus as well. So these are the pole locations. How about the zero location? So there are no zeros, therefore there are no zeros that I need to put over here. And I can start to sketch the root locus directly, as we have done it many times. So first of all, I will start with the part of the real axis that is included in the root locus. So this part is included, that part is included, right, in the root locus. And let's check the number of asymptotes. So the number of asymptotes is equal to 3. And the angle of the asymptote is going to be pi over 3 minus pi over 3 and pi. How about the intersection of the asymptotes? It's equal to summation of poles minus summation of zeros divided by the difference between the number of poles and number of zeros. It will be somewhere, it's minus 7 over 3, right? So let's say if this is minus 7 over 3 is here, let's say, and that will be the intersection of the asymptotes. Maybe I can put it a little bit further, but it doesn't matter for the timing because we are just plotting the root locus roughly. Then the corresponding asymptotes are going to be something like this, right? This will be one, this will be another one, and this will be the last one. So obviously this guy is going to follow this asymptote over here. Right? And those two are going to move towards each other. At a certain stage they will break away and then follow the asymptotes somewhere symmetrically. So that is the root locus that we are dealing with, and we have been asked the specific value of k, where we will have the omega d is equal to 1. So let me sketch the point where omega d is equal to 1. So we would like to find, let's say this is when omega d is equal to 1, I have pole over here with imaginary part having j, all right, and this will be the case. Maybe I can put this on another layer so that I can solve the part B on another layer. I will try to do that. So I will try to add a new layer. Okay, select it and write that. This is the, and this is the pole location that we will have over here. So we can say that let S be equal to alpha plus j. So if at that point S is equal to alpha plus j, then I will have a closed loop system approximately second order with omega d equals 1. Alright? So if I would like to find the corresponding alpha and k value, I will just replace this equation. Anyway, let me add a 0 over there. I will just replace S with alpha plus j in this equation and solve for k bar and alpha. So let me do it over here, down there. So I will have basically, let me write it once again, with another color. So I will have s cubed plus 7s squared plus 6s plus k bar equals 0 when s is equal to alpha plus j. Okay, so let's do that, and I will have alpha plus j cube plus 7 times alpha plus j squared 6 times alpha plus j plus k bar equals to 0. And that will be equal to what? Alpha cube plus 3 alpha squared j and j squared minus 3 alpha and minus j, right? And plus 7 times alpha square plus 14 alpha j and minus 7, right? Minus 7 plus 6 alpha plus 6j plus k bar is equal to 0. Alright, so let's try to, in order to find both alpha and k bar, I do have one equation, but I can equate the real part of the left-hand side and the imaginary part of the left-hand side separately, equate it to 0, and find alpha and k bar values by using those two equations. So let's try to first extract the real part. So this is real, this is real, real, that is real, that is real, and that is real. And the imaginary parts are this, right? So here I have another one, another one, and another one over here. Okay, so from the real part, I do have alpha cube minus 3 alpha plus 7 alpha square plus 6 alpha plus k bar minus 7 equals 0, right? So what I have is from there, and k bar is equal to 7 minus alpha cube minus 7 alpha square plus 3 alpha, so it's going to be minus 3 alpha, right? And from the imaginary part, what I do have there is something like this. I will have 3 alpha square and minus plus 14 alpha plus 14 alpha and plus 6 minus 1 is plus 5. So plus 5 is equal to 0. That's from the imaginary part. By the way, let me check the chat window if you have any questions. Okay, so far so good. Then I will end up with a second order equation for alpha, and I do have the following values as roots of this equation. So one of the alpha is equal to minus 0.39, and the other alpha is equal to, let me write alpha 1 is equal to minus 0.0, and alpha 2 is equal to minus 4.28. And you can replace this alpha value and evaluate the k bar value. And if you do the same thing for both of these alpha values, you will see one of them k bar is negative. So for this guy over here, k bar is negative. So that cannot be a solution. And for this alpha value, if you replace the alpha value over here in this equation, you will end up with k bar is equal to 7.17. Okay. So that's good to go. But notice that we can also verify it somewhere over here, because we know that k bar is going to be somewhere, the alpha value, the minus alpha value will be somewhere over here. So it is very unlikely that that is equal to minus 5 somewhere over there and have the j over here. Right? So this is not very surprising for us. We can verify that. And from there, if k bar is equal to 10k, so from there I can say 10k is equal to 717, and from there k is equal to 0.72. Okay. And S is equal to minus 0.39 plus J. Maybe I should say, since it's the dominating poles and complex conjugate, S1 and 2 is plus minus J. So let's do it this way. So this was for part A, basically. Do you have any questions here? Okay, so there are no questions. How about part B? So now I will remove this layer and add another layer. Let me do that if I can. Okay, so in part B, it says that find K values such that the closed-loop system is approximately second order with psi is equal to square root of 2 over 2. So do you have any suggestions? So how should we proceed this time? So when psi is equal to square root of 2 over 2, what can we say about the theta? And the theta, I'm talking about this angle over here. So if I move at this root locus, this theta is changing, right? And what I mean by theta is this angle. So this is theta. So when psi is square root of 2 over 2, then theta is equal to 45 degrees, okay? So let's say this is my desired point, okay? And here, this is equal to theta, and it is equal to 45 degrees, okay? And if that is the case, we have the theta 45 degrees, then I will have the roots as S is equal to, let's say, minus beta plus J beta, okay, for this one, and the other one is minus J beta. And what I would like to find is the corresponding beta value and K bar value, and I will do the very same thing. So I will write this equation once again, but this time I will replace S with minus beta plus minus J beta. So let me do that over here. So I can write once again S cubed plus 7S squared plus 6S plus K bar is equal to 0, and we're going to replace S with minus beta plus J beta. Is there anything left over here? No. And if you do so, you will end up something like this, right? So you're going to have minus beta plus J beta cube plus 7 minus beta plus J beta square plus 6 minus beta plus J beta plus K bar is equal to 0. And if you carry out these calculations, which I will not do right now, then you will end up with two beta values. Let me write it over here with different colors. So you will have beta 1 is equal to 4.46 and beta 2 is equal to 6.54. And if you find the corresponding K-bar values, you will see something like this. So let's do it over here. Keep the color. So from there, corresponding K-bar value is equal to 2.56, and from there, the corresponding K-bar value is negative. Okay. So Obviously, the negative k bar is not allowed here, so I will have k bar as positive and it is equal to 2.56. So from there, I can also say that k is equal to 0.256. And the roots are as 1 and 2 is equal to, since beta is equal to 0.46 minus 0.46 plus minus j 0.46. Alright, so in the second part we set this angle to 45 degrees, which corresponded to psi value damping ratio value of square root of 2 over 2. And in the first part we are given the imaginary part of the roots omega d is equal to 1. Then we make a parameterization of s as alpha plus j, and we replace alpha plus j here and solve for alpha. And in the second part, what we did was basically we change s with minus beta plus j beta, because it's moving on this line over here. Its real part and imaginary part magnitudes are equal, and we just replace them and solve for k bar and beta. So that was all the things we have done here. Do you have any questions? You are very right, Osman. So you also need to check that the roots are far away. But we already know that when k is increasing, this pole is going to move towards over there, right? So it is going to be to the left of -6. Okay, so it already satisfies the condition of being the dominant poles over here. That the real part is greater than three times the dominant poles over here. So it can be neglected indeed. So we can say it directly by inspecting the root locus, without the need of finding the third pole for that specific k bar or k value. But very good question, Osman. Any other questions?